So our goal is to set up and prove the Baire category theorem. So we need to first of all introduce some definitions. So we'll be working in a metric space, and soon enough we'll specify that this is a complete metric space. But for the moment being, let's assume that we have a set X where a metric D defines the distances between elements of X. So we will say that a set D is called dense. In X, or sometimes we specify and call it everywhere dense in X. If D has a non-empty intersection with every non-empty open set in X. This means that if X is if U is a subset of X which is open and non-empty, then D intersection with U is non-empty. So the standard dense set that, of course, everybody has in mind when one talks about dense sets is the set Q. So Q, as a simple example, Q is everywhere dense in R. In effectively every open interval of real numbers contains rational numbers. It contains infinitely many rational numbers. Also, the set of irrational numbers is also everywhere dense. Okay. Now, the largest sets we can think of, so are the open everywhere dense sets. So conceptually, an open everywhere dense set is thought of as a big. And here we could use a number of non-mathematical adjectives. So we could say big, we could say thick, we could say anything you can imagine. But the bottom line is that these are big sets. And let's give some examples of such sets. So for example, if you take a set like R and you delete all the natural numbers, this is an open dense set. It would be a little more interesting to give another kind of set that needs a little bit of information. So the set of rational numbers, as we know, is countable. This means that we can put all rational numbers in one big sequence. And it's easy to, first of all, I mean, for somebody who has never seen this thing before, it's easy to write all rational numbers in a double array, right? So all rational numbers fit in a double array. Why is that? Just take the numbers that have denominator 1, both positive and negative. You can put them in an array, so you can start with 0 over 1, 1 over 1, negative 1 over 1, 2 over 1, negative 2 over 1, and so on and so forth. And then you can do exactly the same thing. The numerators stay exactly the same with denominator 2, then with denominator 3. So you create a double array that has all rational numbers in it. Okay, of course, a double array is not immediately obvious how it's a sequence, but the very clever classical trick by Cantor tells us that a double array can be put into a sequence. It's the usual diagonal argument, right? You start here, then you go here, then down here, and so on and so forth. And this way you cover the whole double array and put it in one big sequence. So the bottom line is that the set of rational numbers is what we call an infinite countable set and can be put in a big sequence. Okay, so let's assume this for the moment being. And let's consider the following set. Now, this might look a little strange. So take let's call it U sub k to be the following union. So with each of the numbers Qn as the center, we consider an interval of radius 2 to the negative k plus minus n. And so I should subtract it actually here. And let me write it as a fraction so that it becomes a little more obvious that this is a very, very small number, like so. And let's see what is happening here. So what is this set? Okay, so what is this set? We take every rational number and we center an interval on that rational number, and those intervals have smaller and smaller radii. And also the radii start at a pretty small number to begin with. So for example, if you take U10, let's say, the largest radius that you will have in U10 is around the number Q1, whatever that might be, which is 1 over 2 to the k plus 1, 1 over 2 to the 11. So all of these sets are pretty much everywhere dense because they contain the set of rational numbers. If a set contains a dense set, then it is itself dense. And they're open because they're unions of intervals, which are open sets. So all of these are open dense sets. And first of all, there's a simpler reason that needs a little bit more of a background to show rigorously that none of these sets is actually the whole of real line. I mean, some people might look at these sets and think that the rational numbers are so densely located among rational numbers that if you start taking all intervals of all intervals centered at those numbers, but actually quite true. Because what happens is that for each specific k, the lengths of these intervals form the terms of a geometric sequence that has a finite sum. So you can sense from that you don't get as a big set as you might imagine. And of course, you need a little bit of measure theory to justify it, but certainly this is not all the real numbers. In fact, it's a set that has finite measure, and it's a relatively small set compared to all real numbers. And the other funny thing here is one might say, what do you get if you take the intersection of all these sets? Now think about it. Each of these sets has an interval of real numbers centered around each rational number. And the radius of that interval gets smaller and smaller and smaller. A very naive way of thinking about this is that eventually, when you take the intersection of all these numbers, you will just obtain the rational numbers. Well, that's wrong. You will get something much larger. Actually, it turns out that you get a set that, rather than a set of rational numbers, is what we call a set of the second category, as we're going to see right now. So, and that brings us to the Baire category theorem. In other words, the Baire category theorem, among other things, might be used in order to show that this intersection is much larger than the set of rational numbers. So, maybe the simplest statement of the Baire category theorem, and then we're going to look at other statements, and we're going to look at what the word category means, is the following. So we could say Baire category theory. There are many different statements, but let's start with this statement. If X is a complete metric space, so when we say something like this, we assume that the metric in X will be denoted by something, so let's say D, but we don't need to make any particular reference to it, at least in the statement. So if X is a complete metric space, and UN, so we have a collection of open sets from 1 to infinity, is a sequence of open everywhere dense sets. Then the intersection of all of these sets is everywhere dense. Certainly, we don't expect it to be open, but it's everywhere dense. Okay, so it's a big set, and actually, we will see that in some sense, it's even in the sense of real numbers, it's expected to be much larger than just a set of rational numbers. So how do we prove this? Actually, the proof of this, it might seem like a very impressive statement, but the proof actually is very straightforward. So so let V be an open set, an open non-empty set in X. We will show that this intersection of V with all the UNs is non-empty. That's what we need to show. Okay, and the idea here is very simple. Actually, let me try to draw a picture, and then we can write out the argument, and we can complete the proof. So it's interesting that this has such a nice little proof. So imagine that you have the set V here. So this is the set V, okay, which is an open set. And starting with U1, you know that U1, since it's open and dense, it intersects V, and the intersection of two open sets is an open set. So somewhere here, inside the intersection of V with U1, we can find an open ball. In fact, I could by taking half the distance, half the radius of that, I could take it to be closed, of a radius R1. So there exists an X1 and in X. In X and R1 greater than 0. And let's say for the sake of the argument, we can always take R1 to be less than or equal to 1, such that this whole ball, the closed ball, is contained in the intersection, right? In the intersection of U1 with V. And just take a look at the picture. Okay, so now you bring into the picture V, I'm sorry, U2. And U2 is some other set that will intersect the open ball which is contained in this closed ball. So why? Because U2 is also everywhere dense. So U2 intersection with B of X1 R1 has to be non-empty. It's non-empty because U2 is dense and it's open. So now it's the same story. Somewhere in that intersection, you can find another ball. In particular, you can take it to be closed, which is contained in that intersection. So there exists an X2 in X and an R2, which is greater than 0. R2 can be taken to be less than or equal to 1/2, so that the closed ball centered at X2 with radius R2 is a subset of B of X1 R1 with U2 now. Okay, now do you guess what is going to happen? We're going to pretty much at every step bring in one of the U's. So we continue. Similarly, and construct a sequence of closed balls B of Xn Rn, where each ball is contained in the previous one. Oops, sorry about this. And so B of Xn will contain the next ball and so on and so forth. And Rn is less than or equal to 1 over n. And more importantly, B of Xn is a subset, the way we have constructed it, of V intersection with U1, U2, all the way to UN. Okay? So then this sequence of closed balls is precisely what occurs in the counter intersection theorem. So these sets have diameters that tend to 0 because of this condition. They're closed. Each one contains the next one. So their intersection is a unique point. And now, because of the construction, X belongs to V, okay, because of this condition, and X belongs to UN because of the same condition for any n, which means that X belongs to this intersection, and the intersection is non-empty. Okay, it's a really very, very pretty picture and a very simple proof for the Baire category theorem. And now, one of the ways that we use this theorem is by flipping all the sets. So we say that if the intersection of all these sets, the open dense sets, is non-empty, then that means that the union of all of their complements, which are the complements, is what we call closed nowhere dense sets. So these are closed nowhere dense sets. They're closed because they're complements of open sets, and they're nowhere dense. So this, by definition, means that they do not. A closed set is called nowhere dense if it does not contain any open set. So it does not contain any open set. And of course, you may ask, so why does it not contain any open set? Because if it contained an open set, if the complement of this set contained an open set, then the set UN would not intersect that open set, which of course contradicts the fact that it's an everywhere dense set. So it has to intersect every open set. So in a complete metric space cannot be written as the union of a sequence of closed nowhere dense sets. And this is one of the ways that we use this theorem in functional analysis. So alternative statement for Baire's category theorem is that a complete metric space is not the countable union, or I should say the union of a countable family of nowhere of closed nowhere dense sets. In fact, we tend to call sets that are unions of a countable family of closed nowhere dense sets. So sets that are unions of a countable family of closed nowhere dense sets are called of the first category. So, and we also make the convention that a set of the first category is also a set which is a subset of such a union. So any subset of such a union is also said to be of the first category. Now, that means that, and if we call such sets of the first category, then if something is not of the first category, then we say that it's of the second category. So, which sounds like a trivial extension of the definition. So, not of the first category. Then it's of the second category. So in other words, if we are in a metric space, we can ask, is a set a union of closed no-word dense sets, or is it contained in such a union? If the answer is yes, then it's of the first category. If the answer is no, then it's of the second category. And pretty much the Baire Category theorem says that every complete metric space is of the second category. So Baire Category theorem, now you can see why we call it that. Every complete metric space is of the second category. Is of the second category. And I would like to give one more statement that is very, very important, that says the following. So corollary, meaning a simple consequence of that. If X is complete and complete metric space, and K sub n's are closed sets with X being the union of these closed sets, then at least one of them has non-empty interior. At least one of them contains a non-empty, an open ball, I should say. When we define an open ball, the center is always part of it, so it is non-empty by definition. So it contains an open ball. Sometimes one could say that by saying that it has a non-empty interior. By definition, the interior of a set is the union of all open sets contained in that set. And finally, by using the Baire Category theorem, I can show you why that intersection of those strange sets that I introduced before, why this intersection cannot be the set of rational numbers. So I will show you that this statement is not correct. So this intersection cannot be the set of rational numbers. And the reason is very simple, because if you take all those sets, sorry about this, if you take all those sets and their intersection was the set of rational numbers, then you can take countably many sets also that omit one rational number at a time. And such sets, so sorry about this. So you can take also these sets, and now look what is going on. These sets are open and dense according to our construction, right? Each one contains a set of open and dense. These sets are trivially open and dense. because we just omit one element at a time. So these are open-ended. But do you see what the problem is here? If the intersection of these sets was really the set of rational numbers, then by intersecting them with the sets that omit one rational number at a time, this intersection would be empty, right? So in the set of real numbers, which is a complete metric space, we would have a countable family of open-dense sets with empty intersection, and that's simply not possible. So this intersection is not only the set of rational numbers, but it's a much larger set. It cannot even be countable, because if this intersection was countable, then you could really repeat the same argument with an enumeration of that intersection. So this intersection is uncountable. Okay, so it's a very large set. And there are other exciting things that can be done using the Baire category theorem. And certainly that's one of the reasons why the Baire category theorem is one of the theorems of central importance in functional analysis. And that's all that I had for you on this video. Thanks for watching.